So since we've understood memoization and chain rule, let's understand one of the most important algorithms in whole of deep learning. This algorithm is called backpropagation or backprop for short. And this is how it works, right? So first things first, imagine you're given a data set of points xi comma yi, right? What you would do here is you would send each of your points xi as input first. Okay, of course, as usual, just like in every optimization problem, you initialize the parameters. Initialize. So what are the parameters of our problem? Parameters of our problems are these weights, right? So problems initialize wk ijs, right? You initialize all the weights first. How to initialize? We'll learn it a little later in this chapter on what are the various ways of initializing these weights and what works best. For example, let's assume we randomly initialize the weights for now, right? Then you take each of the inputs, right? So you say for each xi in dataset D, right? You send the xi through this network, right? So you input your xi here. Your xi basically has these four dimensions, right? So you input your xi through the network. You just let it pass. So xi gets multiplied with w111. All these the standard way in which everything gets propagated forward, right? So this step here, where you are passing. So you pass xi forward through the network, right? So basically what do you do here? You send whatever is the value of xi1, you multiply it with w111. Similarly, xi2 multiply with w121, right? Because this value here is w121, so on and so forth, and then you apply this activation function, you get this output. Similarly, you take all of these as inputs again, multiply them with these weights, send them to the next layer of neurons. So this is called forward propagation because you're sending this data, whatever data is available in xi, you're sending it forward in the network. Right? So this step is called forward propagation. Because you're propagating this data forward. At the end of this step, what do you get? You get the loss because your data set actually contains xi's and yi's. You've used your xi here. You will use the corresponding yi that you have here. You will use it in the computation of the loss function, right? So you input one data point and you get the loss corresponding to it. Using this loss that you get, right? So the first step is pass xi through forward through the network called forward propagation. This is step 1 or step A. Step B is compute the loss on yi hat and yi, right? yi hat here is what is predicted by this network when you input xi, right? That's what is yi hat, right? So you compute this. Now using this, you can compute all the derivatives you need using chain rule and memoization. As we have discussed in the previous videos, you can compute all of these derivatives. And if you have all of the derivatives, right, the next step is update weights from end of the network to the start. So let me explain what I mean by it, right? What I mean by this is, so you got your loss, right? So let's tick off. So you send your input, the input passes through the network forward, right? It passes through, you get your loss function, and so you've done your forward propagation. Now we'll do our backward propagation, the second part of it. So once I have this loss, I can start computing these derivatives, which means I can start updating these weights right now. For example, I can update this weight W311 new, right? Because earlier the older one is just the randomly initialized one, right? W311 new is equal to W311 old minus eta, which is a learning rate here, times derivative of L with respect to W311, right? And we know that this derivative, again, this is something that we discussed earlier, right? And we know that this derivative here is nothing but derivative of L with respect to O31 multiplied by derivative of O31 with respect to W311. So we can get both these derivatives because we have given the xi point, we have the output. So we can compute this derivative and we can also compute this derivative. Once I have both these derivatives, this is my simple update function. This function that I have here is a simple update function for my W311. Right? This is your simple stochastic gradient descent update, the gradient update, right? With some valid learning rate, right? So first I update W311, then I update W321. So in my backward propagation, what am I doing? When I went forward, I went from input towards output. That's called forward prop. When I'm coming back, what am I doing? Once I got the loss value for the given input xi, yi, I'm coming backwards here. I'm coming backwards. That's why it's called backpropagation. And when I'm coming backwards, and that's when I'm updating my weights. First I'll update this, then I'll update this, then I'll update the weights in the next layer. All of these weights, right? So what's happening here is first my third layer weights get updated, then my second layer weights, then my first layer weights. And during this whole process, I'm using chain rule and memoization. I'm computing these values and storing them here. Right? I'm storing these values here. So the second step here that I'll do, update weights from end of network to the start, right? And this step here is called your backward prop or backward propagation. So literally what we're doing here, if you think logically, is in the forward prop, we are sending the input and trying to compute the output, which is yi hat. The backward prop, we are using the error. Or the loss here to update our weights so that the next time I send this input, these weights will be better tuned to give lesser loss or lesser error, right? So here I'm sending 1 point each, right? So you might say, how long will I do it, right? So because if you look at it, we initialize the weights. For each point, we pass xi forward through the network, compute the loss function, compute all the derivatives using chain rule and memoization, and update the weights. The third step is repeat step 2, right? This is step 2, right? This is stage 2. Repeat step 2 till convergence. We know what convergence is, right? We learned this concept of convergence in the chapter of linear regression and optimization. Right? So what is the concept of convergence? Suppose I have weights wkij. Okay. So first let's assume I ran all of my points. At the end of this step, what happens? All of my data points have been seen once by the network. Because this loop, if you notice, is for each xi in my data set D. Right? This 2a, 2b, 2c, 2d have been run once. Right? But at the end of this running, so when I run all of the points in my data set D once, right? At the end of it, I may still not have converged. What does convergence mean? Convergence means that if this is roughly same as my old at any iteration, right? Remember, this is an iterative step, right? Because I have the for loop here, isn't it? So at any step, if my new weights are very, very similar to my old weights, that means I have converged to a solution. That's what convergence means. We've discussed this in the linear regression and optimization chapter. The same concept of convergence is applied even here. There are some terms that I'll introduce you here, and let's walk through each of these steps. There's a term called epoch. An epoch basically means, so one epoch of training, so it's called the epoch of training. An epoch of training basically means that you have input all the points in your data set once, or you've passed all the points in your data set once through your neural network. So if you pass your data points, let's say if you pass all the points in data D in your data set D, which consists of xi's and yi's once, right? If you pass them through the network, it's called an epoch. If you pass them, let's say 5 times through the network, it's called 5 epochs, right? For example, in this step 2 here, if you notice in this step 2 here, with A, B, C, and D, at the end of each of these steps, what do? You finished one epoch because you're passing each of the points in Xi forward through the network, computing the loss, computing the derivatives, and you're updating the weights. That whole sequence, when you do it for all the points in the data set, it's called as an epoch. And you typically run it through multiple epochs because if you notice your step 3, it says repeat the whole of step 2 until convergence. In the real world, for neural network training, you run the model for multiple epochs. Right? Which means you will pass your data set through the network multiple times. Then you might wonder, how do you pick each of these points Xi and D? Ideally, you should pick each of these points. When you run this loop, when you run one epoch, ideally you should pick your points uniformly at random. Just pick randomly one point from your data set, one after another, and pass it through, do a forward prop, compute the loss, compute derivatives, and update the weights. That whole thing is one epoch when you do it for all of the points, right? So intuitively, if you think about it, what is backprop? If you think about it intuitively, you have first step is initialization, second step is run an epoch, and what are there in an epoch? In an epoch, what you have here is you do a forward prop, then you compute loss, Let me write the forward prop here better. Then you compute derivatives. Again, to compute this, you use chain rule and memoization, and you update weights. In a backward fashion, using backward propagation of weights, right? Then the third step is you repeat these epochs. You repeat step 2 till convergence. That's what backprop is all about. So if you think about it, we know initialization. Initialization is a very standard concept in whole of optimization. Convergence is a standard concept. The most important part of the backpropagation algorithm is chain rule and memoization, because the most important step in the whole of backpropagation is to compute these derivatives, right? And to compute derivatives, you're using chain rule and memoization, except that your forward prop, computing loss, updating weights through backward propagation, all these are standard commonsensical stuff. The most important part here is the chain rule and memoization. So when somebody asks me what is backpropagation, I would say backpropagation is basically a multi-epoch. It's a multi-epoch training methodology where we leverage chain rule and memoization to update weights. Just a multi-epoch approach. That's it. That's all is backpropagation, right? There is a very important, I can't emphasize this more important. This is the most important idea in whole of probably neural networks and even backpropagation. Very, very important idea here is backpropagation type of algorithms. Again, remember, backpropagation is the most important type of algorithm for training neural network. Backpropagation works if and only if your activation functions are differentiable, right? Because if your functions are not differentiable, let's imagine, take this network itself. If these functions, remember these outputs, you get these outputs from these functions, right? Similarly, you get this output from this function. You get this output from this function. If these functions are not differentiable, so if your Fij's are not differentiable, then you can't use chain rule for updating. And if you don't have chain rule, right? If you don't have chain rule, you can't do updating of weights, isn't it? So the most important thing in the design of backpropagation algorithm or in the application of backpropagation algorithm here is your activation functions need to be differentiable. Otherwise, the whole idea of backpropagation and training neural networks goes into the dustbin. If your activation function is not differentiable for whatever reason, if it is not differentiable, that's it. The game is up. So you need to be very, very careful. You need to be extremely careful to know and to design your activation functions in such a way that they're differentiable. And remember, if you look at it, differentiation is the most compute intensive thing that we're doing in this whole thing, right? Passing xi forward through the network is easy. Computing the loss is easy. The hardest part or the most time taking part is computing the derivatives. This is the hardest part, right? And hence, again, updating weights and all is also fairly straightforward. The hardest part or the computationally most intensive part is computing the derivatives. So whatever activation function you have, if it is easily differentiable, if it is not just differentiable, but easily differentiable, if it doesn't take too much time, by easy I mean fast, okay, or if it is fast differentiable, then you can speed up the training. You can speed up the training of the neural network using backpropagation algorithm, right? So two very important things. Backpropagation works if and only if your activation functions are differentiable, and if you can differentiate your activation functions faster and more easily, you can speed up the whole training of the network. It's extremely important concept. I can't emphasize this more, right? Second thing, in our network we saw that we have our input layer, right? You have your layer 1, you have your layer 2, right? So this network, if you see, we have our input layer, layer 1, layer 2, and the output layer, right? So if you look at that network, we have the output layer, right? And you get your yi here. You input your xi here, right? This is what we have had. You have, of course, you have weight 1 here, you have weights 2 here, you have weights 3 here, right? This is a matrix of weights here. Let's not forget that. So one idea people said was, instead of sending one point through the network in each iteration, look at it. What are we doing here? If you look at this code, we are sending one point through the network forward, computing the loss, computing the derivatives, and updating the weights. This takes more time, right? If you send one point after another point. So people said, instead of sending one point through the network, why can't I send a batch of points? A batch of points through the network. Because remember, your derivatives like this, right? So let's take W311 itself. Okay, so the derivative of L with respect to W311, right, can be computed using this chain rule. Now, to compute these derivatives, if you recall our initial discussion on stochastic gradient descent in the linear regression and optimization chapter, we said there are two types of SGD, right? There is straightforward SGD, and there is something called as a mini batch SGD. There is something called as a mini batch SGD, and there is a standard gradient descent. The core difference between these three approaches is, in SGD, you take one point at a time. You take one point at a time and you compute the derivatives to update the weights. In a mini batch, instead of taking one point at a time, you take a set of points. You take a set of points or a small set of points. In a gradient descent, you take all of the points. You take all of the points to compute the derivatives. That's the fundamental difference between all three approaches, right? Right? So you take a set, let's call this set S, which is a strict subset of all of your data points. So you have SGD where you take one point each, where you have mini batch SGD, where you take a subset of points to compute your derivatives, which will be used to update your weights like this. In a standard gradient descent, you take all of the data points to compute your weights. So people said, what we're doing right now through forward pass, backward backward prop, etc., we are sending one point at a time, which is sort of like SGD. This algorithm that we just discussed right now, this algorithm that I just discussed, where I'm sending one point each, this is sort of like stochastic gradient descent, because I'm sending one point each through the network, backward prop. And when I compute the derivatives here, these are computed using just this one point xi. Right? So that's one approach. There is an equivalent approach called mini batch based backward propagation algorithm, where instead of sending one point at a time, you send a subset of points. This set S, this is a set of points, okay, is a strict subset of your data set. And typically, you might wonder what should be the number of points that I should send through the network. That depends on lots of points. That depends on how much memory you have, etc. We'll also look at, so that's called the mini batch size. The number of points, the size of S here is called the mini batch size. Right? Because it is the size of the mini batch that I'm sending through the network in one forward prop and backward prop. Right? You can also do a full gradient descent based approach where you send the whole data set through the network once and then you do it. The big problem here, remember, is keeping all of the memory, keeping all of the data points in memory, in your RAM, right? And computing derivatives and computing all your derivatives, right? Your derivatives using the whole data can be extremely time consuming, right? So people typically do your simple back propagation where they take one point at a time, or sometimes people do a mini batch SGD. Mini batch SGD or mini batch based back propagation, is the most popular approach, wherein you send a subset of points. It's a subset of D, right? You send a subset of points through this loop, right? Through this loop of, again, okay, I have this diagram here. So you take a subset of points, you do forward prop using them, you compute the loss using the set of points, on the set of points, not just on one point, but the whole set of points. Then you compute the derivatives using this set of points, using chain rule and memoization again, and update weights, right? So for example, let's take an example here. Let's assume I have some 10,000 points in my data set. So let's assume I have 10,000 points in my data set. And let's assume my mini batch size. Let's assume my mini batch size is 100. Typically mini batch sizes are like 64, 128, 256, 32, etc. They're mostly they are powers of 2 because of the way mini batch impacts or mini batch leverages the RAM. We'll understand how mini batch uses the RAM when we look at coding examples, right? We'll compute some of this, but let's assume it's 100 for now. Typically you see numbers like 64, 128, 256, 32, etc. Right? Exponents of 2, right? That's what you'll typically notice. But let's assume I have 10k points and my mini batch size is 100, right? So for one epoch, how many loops am I running? I'm running 10,000 by 100, which is, if I run my loop for each, right, for each mini batch of size 100, for each mini batch. So this is my second part, after initialization, for each mini batch of size 100, okay, I'll do forward prop, compute loss, compute gradients, right? Compute gradients and update with backprop, right? So here, what am I doing here? Instead of taking one point at a time, I'm taking a mini batch of size 100. I'm taking 100 points. Now this whole loop will run only 100 times, right? For me to finish this loop, for me to go through all the 10,000 points, because in each of my batches, I'm sending 100 points. I have a total of 100 times I run this loop to compute one epoch, which is a more efficient thing than running this loop 10,000 times with 1 point each in each iteration, right? So that's why mini batch based backpropagation is the most popular approach for training neural networks of all sorts that we'll see in the future.